Okay, hello everyone. My name is Zhang Juntang, and I come from the National University of Singapore. It's my great honor to attend the Open Forum workshop in Peking University. And the topic for my report is simulation of direct initiation of cold char dust cylindrical detonation in the hot air. And the content include the research background, the mathematical model, results and discussion, and finally the conclusion. The first part is the research background. The incorporation of the cold char dust into the propulsion system has attracted a lot of attentions, such as the rotating detonation engines, which cause RDEs. The attention of the cold char dust significantly enhances the fuel detonability and the propulsion pressures, thus facilitating the detonative combustion in the propulsion system. Moreover, the cold char dust have a high energy density. It's easier to store and presents almost no corrosive or cryogenic problems. Except for the application in the propulsion system, the safety hazard for the corresponding to the coal mining explosions also need to be paid attention to. The coal particle explosions generate the flames, the shock waves, toxic gases, and high temperature, high pressure environments, posing serious threat to the personnel and equipment safety. Therefore, the better control and prevent the coal dust combustion, explosion, and or the detonation, we must study the key mechanism like flame propagation and the detonation wave evaluations. And however, there are relatively few studies on the direct detonation of the cold char dust. First, we can say in the experiment, the peak value at the monitoring point 128 proved that the existence of the coal particle detonation. And through the wide-dimensional research under the two different diameters, the pressure can reach 40 and 46 times of the initial pressure. And the pressure peak is very stable, proving the occurrence of the stable detonation condition. Moreover, the addition of the coal particles will increase the explosion pressure and the pressure growth rate. However, these works did not conduct detailed studies on the evolutions process of cold char particle detonation and propagation. So, based on the previous research and the real-world observations, I will outline the motivation and the research objectives. So first, previous studies on the coal particle detonation have not thoroughly investigated the fundamental process underlying the evolution and the formation of the cellular structure. Besides, the research on the cold char particle detonation ignores the effects of the global particle concentrations. Therefore, corresponding to the motivation, we need to study the detailed transients of cold char particle detonation initiation and the evolution of the frontal structure due to the particle detonation interreactions. Also, we should explore the development and the characteristics of the quasi-detonation waves with excessive cold char particle detonations. And next, I will introduce the mathematical model for the whole simulations. And the numerical simulation is completed by the open form-based solver, use the Eulerian-Lagrangian method. And the reference that shows here can demonstrate the effectiveness of the solver. The slide also shows the governing equations for the gas and the solid phases, the particle surface reaction formula, and the interface source terms. The continuous phase is calculated with the Eulerian method, while the particle phase equations are solved with the Lagrangian method. And corresponding to the simplification process, we need to make a further simplify for the governing equations. First, we ignore the particle collisions in the dilute flows. Additionally, a low Biot number indicates that the uniform temperature inside the particles. Besides, compared to the inertial force from the shock waves, the gravity of the particle is too weak to consider. We also assume that the co-particles are spheric and giving a faster propagation speed of the wavefront and the longer relaxation times of the particle reactions, we can also ignore the effect of particle volume variations in the wavefront and assume a constant particle diameters throughout all the simulations. In analyzing the cold Char particles, we focus on the fixed carbon and ash only, ignoring other components like the volatiles. Here are all the assumptions. And in the computations, although there is no gas phase views, the gas phase reactions are still important. For the gas phase reactions, we utilize the GRI make 3.0 to simulate the gas reactions. And the kinetic diffusing limited model is applied for the particle surface reactions. This formula and the parameters are displayed in the table here. And here we make model validations for our simulations. We will proceed with, in our simulations, we utilized a 6.75 one-dimensional domain to mimic the experiment referenced. And it's for us to validate our model and our parameters. The initiation radius of the blast wave is set at 0.31 meters, which is, we can see the red parts. And where the gas temperature T, the P, and the speed of the blast wave, they are all satisfy the Taylor von Neumann set of blast wave solution. The cold Char particles are uniformly distributed beyond the blast wave, with the initial parameters detailed in the table. We can see like the black dots. Here we introduce a concept of a puzzle, wherein it's assumed that all particles within the same puzzle share the identical process, such as the temperature and velocity, to simplify the simulations. Among them, the puzzle revolutions, as shown in the table, represent the spacing between the puzzles. We can see the figure. And the results illustrated in this figure demonstrate that the model can reasonably and quantitatively to predict the detonation velocity of the cold Char particles. And now I would like to introduce the schematic of our detonation simulation. The simulation domain measured of 0.2 meters in both length and width, which is filled with air. We initialized a cylindrical blast wave at the red spot to ignite the detonation wave. The particle parcels are uniformly arranged outside the blast wave. And the concentration of these parcels ranges from the 12 to 1,240 grams per cubic meter, corresponding to a particle equivalence ratio from 0.2 to 20. Addition parameters are detailed in the table. So here we must focus on the 20 equivalence ratio. It's a very high equivalence ratio because we found that the concentration effect has a very significant effect on the detonation propagation. And here I would like to discuss the sensitivity analysis of the mesh. So we can see the left figure. The figures on the left shows the mesh resolution. It's evident that the mesh resolution of 100 micrometers, there is a significant discrepancy in the calculation of the temperature and pressure compared to the other refined meshes. Regarding to the parcels, the result of the 100 micrometers are close to those at the 15 micrometers. However, at the coarser resolution of 200 and 400, the cellular structure becomes more unclear, and therefore, the mesh resolution of 15 micrometers and the parcel resolution of 100 micrometers are optimal choice for the whole simulation. Okay. And the cold detonation leads to the cell bifurcation driven by the solid particles. We began to examine the peak pressure trajectories across the three particle concentrations. In all cases, the overdriven detonation occurs at the early stages. Beyond a critical radius, frontal instability starts, marked by the formation of the clear peak pressure traces. Additionally, with a particle concentration of the 93 grams per cubic meters, the cell becomes finer than the figure A at the 50. Because the sufficient heterogeneous reaction energy release stabilize the detonation. However, at a particle concentration of the 913 gram per cubic meters, the cellular structure becomes less distinct due to the excessive particle absorbing more energy from the detonation waves. And moreover, the detonation cellular bifurcation happens when the frontier radius is large, resulting in the formation of the secondary cells and the transverse wave from the triple points. This can be observed in the enlargement where the one trajectories, the T1 and T2, gradually darken. The evolution of the triple point is displayed here. And here we provide a GIF to show the evolution of the winkles and the collisions. The profile indicates that the particle aggregation and the surface reactions promote new transverse wave generations. And this GIF also shows that shows the evolution. The GIF also shows the evolution of the winkles and the collisions. And here we just provide the particle aggregation and the sparse arrows. Using the enlargement as an example, the two shear layers, the S1 and S2, extend from the upper and lower triple points and behind the Maha stems. Specifically, sparse particle region are filled with vortices from the transverse layers, which displays the particle from the original positions. These regions are characterized by low heat release rate, indicate the relatively low local particle burning intensities and resulting in lower particle and gas temperatures. Here we also provide a evaluation GIF to the continuous layer sparse particles regions due to the various within and between the Maha stems. And here we can see the evaluations of the sparseness regions and aggregation regions. Okay, and here in this article, we introduce the dimensionless parameters C here, representing the mass ratio and the coal to the oxygen. To demonstrate the variations in the average cell wise and the shock wavefront velocity, the Kc is related to the particle concentrations. So here for the first figure, the left figure A, the red line, we can see initially the average cell wise decreases, indicate that the more coal lead to a greater energy release and a smaller cell size. However, subsequent increases due to the cell bifurcation. And besides, as the Kc increases, the average shock speed of the stable cellular detonation initially rises and then decreases, aligning with various experimental results. And besides, from the Kc and the corresponding ratios between the particle concentrations, we can also categorize the detonation types based on Kc. We will explain the specific reason for this classification later, such as the stable detonation or the quasi-detonation cases. And regarding the detonation speed under the different concentrations from the figure on the top, we can see the shock speed decrease rapidly beyond the initial blast wave locations to exit from the overdriving conditions, marked by the initiation of the speed oscillations due to the multi-heated front. In the quasi-detonation cases, we can see the blue lines. Here, the shock speed is about 48% lower than in the other two cases. And in the previous pages, we distinguished the concentration ranges of the stable concentration of the quasi-detonations. Here we make comparisons. We can find that the phi here, the phi in the bottom is the global equivalence ratio. We can find that the non-uniform distribution of the particle occurs behind the wavefront. And besides, when the concentration is 93 gram per cubic meters, the gas, particle temperature, and heat release rates in the sparse particle area are relatively low, while the mass fraction of the oxygen is high. However, when the concentration is 913, the opposite conclusion is obtained. Besides, when the concentration is 93, the subsonic region, we can see the figure F in the both figure. The subsonic region is continuous, while in the quasi-detonation conditions, the 913, the subsonic region is discrete. Moreover, the quasi-detonation propagation is featured by a series of small azimuthal detonation waves. We can call it the ADW, and namely from 9 to 8. We'll make an enlargement here. So ahead of the individual ADWs, a narrow induction zone can be observed, filled with shocked but unburied particles. Above the domain diagonal, the ADW124 are propagation downward. Nevertheless, for the 7, 8, 9, below the diagonal, they are moving upward. Collision of the ADW are also observed. So in the quasi-detonations, the subsonic and particle sparse regions are only limited to the post-azimuthal detonation waves flows. This is very significantly different from the gas phase detonation. And so in the detonation process, regardless of the initial configurations, whether in the shock tubes or the cylindrical conditions, or fuel types include the gases, droplets, or particles, a consistent set of the structure featured such as the Maha stems, the incident waves play crucial roles in sustained detonation propagations. While the triple point has also been replaced by the interaction of ADWs in the quasi-detonation conditions. Besides, the temperature distributions behind the quasi-detonation waves is non-uniform, exhibiting a difference nearly 2000 Kelvin, with notably higher temperature near the ADW. This phenomenon does not exist in the other detonation conditions. Okay, and now we can make an overall comparison of the effect of particle concentration on the detonation wavefront. First, by analyzing radial average parameters distributed as various particle concentrations, we found the induction distance of the concentration for 50, 93, and 930 grams per cubic meters are 2.5, 1.3, and 3.2 millimeters, respectively, indicating that the induction distance firstly increases and then decreases. Additionally, the Maha number for the concentration of 913 grams per cubic meter exceeds 1. We can see the figure C. The figure C is larger than 1. It is suggesting that the most of the area behind the wavefront cannot enhance the leading shock waves or supporting the self-sustained detonation. Furthermore, the thickness of the shock zone at the 93 is 40.6 millimeters, greater than the 30.8 millimeters observed at the 50 grams per cubic meters. The differences is attributed to the non-uniform distributions that brings some local particle-oxygen mixture closer to the stoichiometric ratio. Okay, now I would like to make a conclusion. Firstly, the gas particle two-phase detonative combustion is simulated with Eulerian-Lagrangian method developed from the open form packages. And besides, the flow jet and the vortices form the strong shear layers and expel particles from the original locations, lead to a non-uniform particle distribution, forming particle spars and aggregation regions and result in the highly non-uniform heterogeneous detonation. And thirdly, the particle concentration significantly affects the detonation propagation. The average leading shock speed firstly increase and then decrease with the increased particle concentration, while the average cell-wise first decreases and subsequently increases. Fourth, under the quasi-detonation, a series of the azimuthal detonation waves in the discrete subsonic region maintains the propagation of the detonation. This is significantly different from the gas phase detonation. At last, the average Maha number for the quasi-detonation exceeds 1, indicate that the majority of the region behind the wave front lacks of the condition necessary to sustain the detonation wave propagations. Okay, and thanks very much for your attention, and this is my report.